Okay, so my mini course is I gave the title of Random Covers of Hyperbolic Surfaces. It can equally have the title of Random Permutations from surface groups. And this is based on a joint project with mostly with Michael McGee. So, I mean, probably about 4 different papers. And I wrote down a rough outline of the mini course. So first I'll start, this will be mainly today. So this is probably talk number 1. So I'll talk about random covers, about the model, the random model that we are analyzing, how it's related to random permutations, and I will discuss the main results of this project. And then I will show you something that came before this project, which is analogous questions for graphs instead of surfaces and free groups instead of surface groups. And explain why surfaces are harder. And this should probably be, let's say, 1/2 of second talk. And then this will be the longest part of the talk. Will be actually a crash course on representation theory. I don't assume any background in representation theory. So I want to give you some basic facts about representation theory and how this is used to answer some of the questions that I will propose today. So this will probably take around so 1/2 of second talk and the third talk. And then the last talk, hopefully, I mean, there might be some carry, but so fourth talk, we'll see how representation theory actually leads us back to a combinatorial definition of surfaces with a nice boundary, and then we need to work with this. Okay, so I'll start now with the first part, so the introduction. So I'll talk about random covers and random permutations. Okay, so this workshop is called, has the word random inside, in the title. So why do we care about random objects? In general, I think there are roughly, I think, 2 main reasons, perhaps there are more. One is that we want to understand a random object gives you a sense of what is the generic behavior of this class of objects. And another usage for a random object is that sometimes we want to prove existence of certain objects, and we use the probabilistic method. We show that there is such an object by showing perhaps that the expected value is, we want to show that there is an object which satisfies, such as a function has at least a certain value. It's enough to show that the expectation of this function is at least this value. Therefore, we know that there is such an object. So oftentimes, to show existence of object, we use the probabilistic method and show that there is that random objects actually satisfy this property. And a useful model for random objects is, so a useful model for random objects is the model of random covers. So when I say random cover, I mean topological covers. And this is true. So what kind of objects? So you can have in mind graphs, and we'll talk about graphs. We'll talk about surfaces. We will not talk, but you can also think about 3 manifolds. So all kinds of topological categories of objects. And the model is you fix, so you fix an object X in this category, so it could be a graph or a surface, and you take and you consider a random, let's say, n cover. So I'm going to use the word cover for topological cover space, topological covering space, and n cover, this is n sheeted covering space, okay? And the key fact here is that if X is a nice space, so nice, I mean connected, locally path connected and semi-locally simply connected, but all the spaces that we're talking about are nice. Then there is a one-to-one correspondence between, on the one hand, n covers of X, and on the other hand, homomorphisms, the set of homomorphisms from the fundamental group of X and the symmetric group on n elements. Okay, now this is, I left here some space. I mean, this is not an exact, this statement is not true, as I said, it's not exact as I stated it. So there is something missing. But what is missing is that these n covers should come. So perhaps if we put here a base point in X, so if X has some base point, then I also want, so it's an n cover, so above the endpoint, above the base point, we have n different points, and I need to label them by the numbers 1 to n. Okay, so with a bijection between the fiber above X naught and the numbers 1 to n. So when I write n in brackets, this is just 1 to n. Okay, so let's explain this correspondence, this 1-to-1 bijection. So I want to start by, first I want to explain this direction, this implication, okay? If I'm given an n cover of a space, what is the homomorphism I get to Sn? Okay, this is all, these are classical facts from algebraic topology, but I want to remind you of this. So how, if I am given so imagine I have this is now X, this is my space, here is my base point. And now I have some cover, this is an n cover. An n covering space, and now I have n points. This is the fiber above X naught, and I label it by the numbers 1 to n. Okay, this is the bijection. Now I want to define a homomorphism from the fundamental group to Sn, which means that for every element, for every element of the fundamental group, every closed path here, let's call it gamma, I need to specify a permutation, right? So what do? I simply lift gamma to all these points. So I can lift it, for example, from the point I. If I try to lift it here, I'm not necessarily going to get a closed path, but I know that the end of the lift will end in one of these points. Okay, so it would end, if I try to lift gamma, it will end in one of these fibers. And if it ends in J, I'm going to say that the permutation of gamma, so gamma is mapped to a permutation that maps I to J. Okay, this gives me a permutation. So I'm saying that, so in this case, gamma maps, okay, Okay, the permutation. Associated with gamma maps I to J. Okay, and now you can check that this is indeed going to be a homomorphism of the fundamental group to Sn. First of all, this is a permutation, obviously. And if I concatenate here path, it will concatenate the permutation. Okay, so this is indeed a homomorphism, even though there is one remark I need to put. So for this to be a homomorphism, the way we are going to multiply permutations is from left to right. Okay, so we compose permutations. Okay, now, so the reason is that when we think about the fundamental groups and in general, more generally, KD graphs, we usually multiply from right to left, from left to right. And, but you really don't need to worry about it. It's not going to change anything dramatic in the top. But it does mean that the way I'm going to, if sigma is a permutation, my notation will be 1 to the sigma this is the image of 1 through sigma. And this works better when we compose permutations from left to right. Okay, so this is by definition, this is sigma of 1. Okay. Okay, so notation-wise, I'm going to okay, so notation, I write it here, but again there. So if I have a homomorphism here, phi, I'm going to map it to x phi here. Okay, so notation-wise, notation, the cover corresponding to phi, which is a homomorphism from pi 1 to Sn, is denoted x phi. And I will, so there is also a general way, I explained to you how to get from here to here. There's a general way of getting from here to here, but it will be more efficient or more useful to describe it when we get to the actual axis that we are studying here, okay? So I will explain this other directions soon for the specific cases. And good. Okay, so we have two setups. Let me write them here. I mean, two main things that we will study. Yeah. No, so I always have covers with a labeling of the points. So I can have the same cover. If I change the labeling of the points, it will be a different element of this set. Okay, so the labels are given with the cover. Okay. Any further questions? Yeah, please feel free to interrupt me. Yes, I want to discuss the two main setups for this talk. Right, okay, yeah. Yeah, we'll discuss it. Yeah, I'll say a bit more about it, but notice that in this this cover may be disconnected, right? In fact, for example, I can map the entire fundamental group to the identity. Okay, this is a legitimate homomorphism. And then you see that the cover must be just n different disjoint copies of X. Okay, so I can take n disjoint copies of X. This is a legitimate cover, and which corresponds to the trivial homomorphism. Yeah. You can take, to get from here to here, you can take the universal cover, n copies of the universal cover times the points 1 to n, and then you take some diagonal action and you mod out. Yeah, but I think when we talk about specific setups, it will be much more down to earth to understand how it works in these specific models. So, okay, so I want to keep a table of okay, so I wanted to talk about two axes here in this talk. One will be just a graph of an 8-loop and just a bouquet of two petals. And the other one is the genus 2 orientable surface. Okay, these will be our two objects. Okay, now the fundamental group. Okay, here, of course, this is the free group on two generators. And I want to denote it by, I want to denote the generators by A and B. Okay, and here it's the fundamental group of the surface. And I want to take the following presentation, the canonical presentation, where I have 4 generators and 1 relation, which is the product of commutators. Okay, and I should say, so I'm going to use this as an examples, but this, what I'm going to say about this group and graph is general for any graph and every free group. So this is so in general, graphs and free groups. And here, the general picture, this is what I'm going to say here is true for any gamma G. So the fundamental group of genus G surface, orientable surface with G at least 2. So I want the surface to be basically to have a hyperbolic metric on it. But yeah, so the genus here should be at least 2, and it should be orientable, but orientable is, I mean, genus at least 2 is important. The fact that it's orientable is only because this is what we did, and we didn't yet analyze the non-orientable case. I don't think there is an issue there. Okay, now, so now we want to take covers of this. What is this set even of homomorphism from the fundamental group to Sn? As a set, what is it? So here I just need to take the generators to the symmetric group, right? And there are no, this is a free group, so this is the set is the same as, if I fix a basis, this is the same as taking any pair of permutations from Sn, okay? While here, of course, if I want to map this to Sn, I need to take 4 permutations which satisfy this relation. So these are all the 4 tuples of permutations which satisfy this relation. Okay, and an important thing here is that so in this model, notice that we have, I mean, because our fundamental group is finitely generated, this set is always going to be finite. Okay, if pi 1 x if pi 1 x is finitely generated, then there are finitely many homomorphisms from the fundamental group to Sn. And therefore, we can take uniform measure. Okay, so we can pick a homomorphism or equivalently an n-cover uniformly at random. And this is what we are going to do. This is our model. Okay, so now let's see how do we construct. Now what I told you, I want to explain how to construct given a homomorphism, how do I get an n-cover? Okay, so perhaps I'll do it here. Okay, let's start with the graphs. So with the graphs, it's pretty easy. I think about this graph as having here this is my graph with labels A and B. And then to get a cover from a homomorphism, I just draw endpoints. I label them 1 to n. And then I have a permutation A, right? I have a permutation corresponding to A. I'm just going to draw the arrows of this permutation. So if A takes 1, 2, 3, I want to draw this edge, and then perhaps this edge, and then this edge, and perhaps 2 is a fixed point, and so on. Okay, and this is for A. And for B, I get a similar picture. Perhaps 1 is a fixed point, 2 goes to 3, and 3 goes to 5, and 5 goes to 6, and 6 goes to 2, and so on. Okay, and this will be my cover. So it's a very natural. This is, by the way, it's also, you can think about this is also a Schreier graph, if you know what a Schreier graph is. So this is the cover in the case of free groups and the graph. And what does it look like for surfaces? So for surfaces, I also want to get some combinatorial picture. So what I'm going to do is to, so this is my space. What I want to do is to get it to build it from an octagon. So I have this octagon, which I'm sure all of you know. Okay, so this is an octagon where, again, I have here A, B, and C, and so on. And so how do I get this from an octagon? I just glue together the A to A and B to B and so on. This gives me, and here I get, okay, I will not do it with the colors, but I get something like that. Okay, so this is actually this is the same picture. So how do I get a cover? So for a cover, I take n copies of this octagon. So I get n copies of this octagon. So n copies. And now I label this, I take this vertex, which corresponds, this is the first vertex of my relation. And I label this vertex by 1 up to n. And now, remember, this is the edge A. So what I'm going to, so this vertex should be 1 to the A. This edge is B, and this vertex will be 1 to the AB. So I compose AB, and this one will be 1 to the AB, A inverse, and so on. And then how do I make an N cover from these N octagons? Okay, I just glue again an orientable A to a non-orientable A, but only when the vertices match. Okay, so here I have, for example, 1 and 1A. There's going to be some other octagon in the mid somewhere. Sorry. Okay, this is my this is the reversed A. So in one of these octagons, I must have here the point 1. Okay, this is an easy exercise, and this will be 1 to the A. Okay, perhaps there will be here some I, and this is I to the A. Yeah, okay, so one of these octagons is going to have an edge 1 and 1A, and then I'm going to glue this edge together with this edge. Okay, and why do I know that this actually works? Why can I label the vertices like that? 1 to the A, 1 to the AB, and so on, and then close the cycle? Why does it work out that after 8 steps I go back to 1? Yeah, because these permutations satisfy this relation, okay? After the product of commutators is the identity. Okay, so it works out well. So I glue together these N octagons and I get my cover. Okay, so this will be the model. So just to keep this in mind, I'll put it here on the table. So just for a reminder, and here I hope this reminds you of these pictures. Okay, any questions about this model? Right. Yeah, so you're asking about if it's still orientable? Yeah, so because I always glue together, this is an orientable A, and this is an A with the opposite orientation, it all works out. I mean, if this is oriented like that, then because I glue, I glue edges always with opposite orientations, I preserve the orientation overall. Okay, so the second remark is that, okay, so there was earlier we said that this cover is not necessarily connected, but when is it connected? So in terms of the homomorphism, how do we know whether the cover is connected when we only see the homomorphism to the symmetric group? How do we know? Yeah, exactly, good. So the image of this group, so the image of the group, gamma 2, the fundamental group of the surface, this is a subgroup of Sn, and it should be transitive. Okay, because only if it's transitive, you can get from every point here to any other point. And if it's disconnected, there are going to be different points in different connected components. Okay, so you can think about this afterwards if you don't see it. And we can ask whether, okay, so in this model, are these the objects we get usually connected or not? This is one key feature. So is X phi usually connected. So namely, the image of this group is usually connected, okay? And so I'll write it here, is X phi connected. Okay, and does anyone know? So the question is really, I take a free group, and I take a random homomorphism to the permutation group, to the SN. Or in other words, I take two random permutations. Do they generate, in general, a transitive group? Okay, so the answer is yes, and this is actually a classical work of Dixon. Yes, and so in fact, I mean, okay, of course not always, but randomly. I mean, so in fact, he showed, Dixon in his work showed that if you take two random permutations in SN, they usually generate at least the alternating group. So it's not only transitive, but it's much more than transitive. It's actually almost the entire group. So the image is at least the alternating group. Okay, so asymptotically, almost surely, okay, this just means that the probability, as n grows, the probability tends to 1, okay? Okay, so this is a classical result. Here, there is also a result, and in fact, there is a parallel result. It's perhaps not as classical, but Liebeck and Shalev, this is a result from 2004. They basically show that the same holds here. So again, not only this surface is usually connected, or the image of this group is transitive, in fact, you get almost the entire alternating group. So phi of, sorry. Yeah, this is not gamma 2, here it's F2. And here it's gamma 2. And again, it is at least AN, asymptotically almost surely. So in particular, this group, the surface we get is asymptotically almost surely connected. This work, by the way, they dealt with all Fuchsen groups. So they know exactly for which Fuchsen groups this is true and when it's not. And it could be that for this particular group, this result was known before, but I don't know of. I think this is also the first time it was proven for this group. Okay, and
you had mentioned that X is also sometimes.
Yeah, I don't think it's known. Okay, I mean, I know myself very little about these questions when it comes to three manifolds. Okay, I don't know of such a result. Any other questions? Okay, so okay, the third remark, and we're going to say more about it later, is about the size of these sets. Okay, so here, of course, the size is obvious. It's just n factorial square, right? But what is the size here? How many 4 tuples? Yeah. Here it's uniform, yeah. Yeah, so throughout this talk, yeah, I'm going to, this is uniform over this set of homomorphism, yeah. So what is the size of this set? Okay, so what is the size of, what is the number of homomorphism from this surface group to Sn? Right, okay, good. So it should be roughly, right? We have 4 permutations and you have 1 restriction. So it makes sense that it's roughly n factorial cubed. And this is indeed the first, so Sn cubed this is the first term, but there is an error term, okay? It's not precisely, it's not a linear set of equations. And it turns out, and this was known since Frobenius, that the error term comes from representation theory. And we'll discuss it in more details tomorrow. So it turns out that the error term comes from going over all irreducible representations of Sn. And you need to take 1 over the dimension of this irreducible representation squared. Okay, this is the kind of magically representation theory comes into this. And this is, okay, this equality is not there. This has nothing to do with Sn actually. This is true for any finite group. You can replace here Sn with any finite group. And this is basically known to, this is, I mean, Frobenius knew everything one needs to know to prove it. But I think it was explicitly written by Hurwitz in 1902. This is fairly classical. As classical as math can, okay? And this is again general for Sn. Now this feature here is sometimes called Witten's zeta function of a group. So when, okay, zeta function, when instead of this 2, you put some s here, you put a variable, 2 is this is a variable. This is called the Witten zeta function of the group Sn, or in general the group G. And this was known by, and this is, okay, so for those of you who know some representation theory of Sn, again, we will discuss it in more details tomorrow, you see that the main contribution comes from small representations, right? So representations of small dimension give you the highest contribution. What are the representations of smallest dimension of Sn? Yeah, there is a trivial and there is a trivial representation which is one-dimensional and okay, and the sign. And the sign is also one-dimensional. So both of these give you 2. And it turns out that this is the limit, okay? So as n tends to infinity, this is 2 for Sn. And this is a result of Lulov from 96. Okay, so we'll discuss, okay, anyway, so you should think about this is roughly twice Sn factorial, okay, roughly. And we'll discuss this, these 2 results tomorrow. Okay. Okay, so now, okay, so now I want to discuss, first I'll call it 1.2. So I talked about generally about the model, but we are going to study something more specific about the models. So not the image of the entire group, but rather more local statistics of these models. And these are going to be closed path or geodesics and fixed points. Okay, so our next goal we're going to fix some element gamma either in the free group or in the surface group and study the number of fixed points of the permutation corresponding to gamma. But notice that, so I'll write it like that. So fixed gamma of n, this is just the number of fixed points of the random permutation which is the image of gamma through the homomorphism. And this is, notice that this is a sequence of random variables. Okay, where n is the parameter. Right, and here again, so here phi is a homomorphism from gamma 2 or from F2 to Sn, and it's uniformly random. Okay, so this is what the randomness comes from. And what is the motivation? So I want to say a few words about why we study these objects. So for me, there are roughly four sources of motivation. I will say very briefly, I will mention three of them very briefly and say a bit more about the fourth one. Okay, so first, there are questions in free probability. And in fact, one of the results I'm going to tell you about soon, at least in the case of free groups, was studied by a free probabilist, okay? The second motivation is that from the experience we have so far, there is actually a deep structure. When you start looking at this question, you see a deep structure. So a very beautiful and elegant structure that you unveil when you start studying these kind of objects, random variables. There are also questions about the profinite topology and profinite rigidity of free groups and surface groups, which you can approach via studying these objects. Okay, and again, I'm not planning to say more about this, but the fourth one is spectral. There are spectral questions. So you have questions about the random objects, spectral questions that you can translate to questions about number of fixed points and closed path. And this is, I want to explain a bit more where this is, what is the source of this connection. Okay, so let's start with graphs. So let's assume that A is the adjacency matrix, also n by n adjacency matrix of a graph on n vertices. And you want to study the eigenvalues of A. So A is a symmetric matrix. It has real eigenvalues. So eigenvalues are, let's denoted by λ1 up to λn. These are all real eigenvalues of A. And you want to study them. There are many properties of the graph that you can read from this spectrum and so on. So there is a very basic formula, a very elementary formula, which tells you that if you look at the some t power of A, and you look at the trace of it, so in terms of the eigenvalues, what is this? Yeah, okay, it's the sum of all eigenvalues to the t on the one hand. On the other hand, this is an adjacency matrix, right? So the trace of A to the T is actually exactly the number of closed path of length T in the graph G. So for many questions, if you want to understand these, the eigenvalues, you can count the number of closed paths in the graph for various values of T. And this can teach you a lot about the eigenvalues. So this is for graphs. And in hyperbolic surfaces, so if you have a surface with an hyperbolic structure, metric, you have an analog formula in the given by Selberg. So there is a famous formula of Selberg. Which gives you a similar connection between, on the one hand, eigenvalues of the Laplacian, and on the other hand, closed geodesics of on the surface. So so it provides, I will just write that it provides a similar connection between eigenvalues of the Laplacian. So the Laplacian operator on the hyperbolic surface, and okay, not exactly the number, but some function on closed geodesics of some bounded length, of some of length. Let me write of length at most L. Some L, okay. So you get this connection, and yeah, okay. So I think I explained to you why we're interested in counting why spectral questions about the spectrum of graphs or surfaces leads to questions about closed path or closed geodesics. But what is the connection with fixed points? Okay, so what is the connection with fixed points? So this comes from a simple observation, which has to do with our model. Okay, so let's talk about surfaces. So this is our base surface X, and this is our cover. This is the end cover. And now we want to analyze closed geodesics here. And if we look at some, let's say this is a geodesic here, and we project it to X, then we get, okay, but before that I should say, I mean, I didn't say it before, but if X is a hyperbolic surface with a certain metric, we can also pull this metric to the cover, okay? So we get a random hyperbolic surface in this. So there is it's very, yeah. So now you think about X as a hyperbolic, and also the cover is a hyperbolic. And with this, if we have a closed geodesics here and we map it by P to X, we're going to get a closed geodesic here. Okay, so if you want to analyze closed geodesics in the cover, so every closed geodesic in the cover projects to a closed geodesic here. But now we can reverse the direction, and we can say that to study closed geodesics in the cover, we consider all closed geodesics in X, and for each one, let's call it delta. Let's denote by delta. So now I fix one geodesic here. How many geodesics here project to it? Okay, so if let's perhaps take a simpler picture. Okay, let's take a simple picture. Let's say I take this. This is a geodesic here. This is now delta. This is a closed geodesic. How many geodesics in the cover correspond to delta? Okay, so well, yeah. So what I can do is to I choose a point here. Okay, then I have endpoints above it, and I can try to lift delta. So if I can, this is what we did before with an element of the fundamental group. I can also do it with delta. Now, if I try to lift it, then either I get an open geodesic, and then it doesn't correspond to this geodesic. It's not a closed geodesic, or I can get a closed geodesic if it closes, right? And the number of closed geodesics is therefore the number of fixed points in the permutation corresponding to delta. Okay, but so just notice that, okay, delta is not necessarily an element of the fundamental group, but it is a well-defined conjugacy class in the fundamental group. Okay, so so delta corresponds Yes. Right. Right. Yeah. So if it's not a fixed point, yeah. So perhaps it would look like that. Perhaps here it's a cycle of length 2. Then it will not correspond to delta. It will correspond to delta squared. Okay. So yeah, it's going to go over delta twice. So it will correspond to a power of delta, not to delta itself. So in general, delta is not an element of the fundamental group, but it does correspond to a well-defined, to some conjugacy class. Let's call it gamma in gamma 2. And then the number of fixed point of delta is the same as the number of fixed point of gamma, okay? Because, and then, okay, and the number of closed geodesics in the cover in X phi, which corresponds to delta, is the same as the number of fixed points of the image of the permutation corresponding to gamma. Okay, again, because the number of fixed points is invariant under conjugation in Sn. So if I take, it doesn't matter which gamma I take from this conjugacy class, the number of fixed points is the same, right? Right. So in general, yeah, and regarding the question, I mean, it's a bit weird that I only care about. It seems like, okay, so what? So the other geodesics here are correspond to larger powers, but usually I only care about geodesics, short geodesics. So most of these longer geodesics will not even be in our counting. Okay, so it all works out well. I mean, this. Right. Yeah. So if I understand correctly, you're saying, I mean, this is only here I only deal with this particular geodesic, or only with one geodesic, the one corresponding to the conjugacy class of gamma. But in general, to use such formulas, I need to talk about all closed geodesics. And indeed, I mean, so I'm going to tell you about, in these talks, I'm going to tell you about what happens for a given element to use it through the Selberg formula and get the results of our spectrum. You actually need to get some uniform, you need to analyze together what you get for every element or every short element of your group. So this is why it's more complicated, but we're not going to discuss it this week. Yes. Yeah, so perhaps okay, I just want to, before I move on to talking about the results, I just want to mention very briefly what kind of results we can get. Okay, so with the results, or using or relying on the results I'll mention, one can show, okay, so you can show, okay, one can show. Okay, this is perhaps rather, okay. One is Broder-Shamir type result. This is from 87. This is in the graph case. So for graphs, if you just look at the results that I'm going to mention right now, you can show that a random irregular graph has the second eigenvalue of the adjacency matrix, lambda 2. This is the second. So the first eigenvalue is always D. I don't want to go into this. And the second eigenvalue is at most D to the 3/4, asymptotically almost surely. This is not the best result, but this was for the time it was the best result. I mean, now we know a much better result. Friedman proved that this is actually 2 square root of D minus 1 plus epsilon. Okay, but for surfaces, so this is together with Michael and with Frederic No. And this is okay, it was published last year. So we can show that a random n cover of a fixed hyperbolic surface, orientable hyperbolic surface, has all new eigenvalues. Okay, so has all new eigenvalues, at least 3/16 minus epsilon. Okay, so in this model, if the base surface has eigenvalues, you never get rid of them. So you can only say something about the new eigenvalues, and we show that there are at least 3/16 minus epsilon. And here, the conjecturally is that you can replace the 3/16 with the 1/4. This should be optimal. And by the way, so one of our goals, original goals, was to prove, I mean, it is not even known, not whether random surfaces have this property, but whether you actually have any surface with the genus tending to infinity. So it was open, whether you have any sequence of surfaces with genus tending to infinity, such that the spectral gap of the Laplacian is very close to 1/4. So this was solved by Michael after this work with using a not completely irrelevant, not completely different model, but different model. So basically, instead of using closed surfaces, he used open surfaces. And then the fundamental group is free, and you can use the much better results we have here. And then you can make the open surfaces again. You can make them. You can make small changes to make them closed. Anyway. So. Okay. Sorry? Ah, right, yeah. Yeah, and the 316 appears in. Yeah, by the way, the same result later. So for hyperbolic surfaces, you also have a very natural model of the Weil-Peterson volume. There is where you can actually see. It's a very natural model where you actually see all hyperbolic surfaces of a given genus. Here you notice that we only get a discrete set of surfaces of any given genus. And after this work, there were two teams who proved the same results in this other model, again with the 316. So I think the 316 has something. I don't know. When you do the math, you see that it's the first. It's the first step. If you do the first step right, this is what you get. It comes from the. I don't know. Yeah, that's from the numbers, and it's also the same thing. It's exactly the same. It's the same 3/4 here. It's the same number in these guys. Okay, so I want to end. Sorry. Yes. Not the fixed point, but no. Even though the results I'll state, we know them for any fixed length of a cycle. No, but they don't play any role. Okay, so I want to end this talk with today's talk by telling what are the results we have for these random variable fix. Okay, so I want a short warm up. Okay, and so we're not going to, again, to simplify my presentation, I will not discuss in general the random variable, but only the first moment, only the expectation. So in this talk, we focus on the expected value of this number of fixed points. And I want to start with a warm-up. If sigma in Sn is uniformly random, okay, what is the expected number of fixed points of sigma? Okay, how many fixed points does a uniformly random permutation have? Okay, so what's the answer? Yeah, 1, right? Why? Because what is the so we have okay, this is the random permutation. What is the probability that this is a fixed point? 1 over n, right? The image here is a uniform, So there is 1 over n probability that 1 is a fixed point. And this gives you 1 over n to the expectation, but this is true for each one of the indices. So you get overall n times 1 over n, which is 1. Okay, and by the way, this is true for every n. What if you take the square? Okay, let's take the 6. Now I take a uniformly random permutation, but I take the 6th power of it. What is the expected number of fixed points now? Okay, so let's see. Let's do the same. If I want 1 to be a fixed point of sigma to the 6, then what is the cycle length of 1 in sigma? Okay, so when is 1 a fixed point of sigma to the 6? If and only if 1 is contained in a, okay, it's a 1 cycle, a 2 cycle, or a 3 cycle, or a 6 cycle, okay? So these are the 4 options. If 1 is in one of these options, then we take the permutation to the 6, you get a fixed point. And for Sn, the distribution of the cycles of the cycle length of a given element is uniform between 1 and n. Okay, so you get each one of these happens with probability 1 over n. So overall, the probability that 1 is a fixed point is 4 over n. And in general, and then you get you get the same contribution from every index, not just from 1. So the answer here is 4. But this is only true when n is at least 6, okay? Because otherwise you don't get this 6 cycle. Okay, and more generally, if I take so the general answer here is if I take a Q power of a random permutation, the answer by the same argument is the number of Q of divisors of Q, and this is true for every n, at least Q. Okay? Okay, now I want to state okay, so now I want to state the analog result here about the expected number of fixed points in the image of a given element. So here, let's take an element in the free group, which is not the identity, and let's write gamma as gamma naught to the Q, where Q is at least 1 and gamma naught is non-power. So I want to write it as a power of a non-power. And then this is the result of Nika, of Alexandru Nika, from 1994. He is the free probabilist I mentioned before. So he has, there are 2 results. First, this expected value of fixed points as n tends to infinity, we get the same answer as for uniform random permutations. We get that this is the number of divisors. It tends to the number of divisors of Q. And the second result is that this is Okay. Let me write it like that. There is a function of n. So there is a rational function of n such that the expected number of fixed points is equal to this function for every large enough n. In fact, you can take any n at least the length of the word. Okay, and I'll give an example. So if I just take A is my generator. What is the expected number? What is the expected number of fixed point of A? Okay, so notice that A, it is just mapped to a uniformly random permutation, right? A and B are the generators. I just map them to uniformly random permutations. So it's the same question that we had before. So this is exactly one. And a slightly more interesting result, I'll take the commutator of A and B as an example. It turns out that this is going to be 1 plus 1 over n minus 1. And we'll explain tomorrow how to prove this result and why, and specifically how to get this example. Okay, so you see you get a rational function. This is a rational function in n. This is the second part, and the limit is 1, which is the first part. And okay, now what happens for surfaces, for surface groups? So here, let's take again an element of the surface group. Again, I want to write it as a power of a non-power. And this is the result of Michael and myself. So we worked pretty hard, and then it turned out that for this first result, we just get exactly the same answer. So exactly the same. Even though the proof that we know is much harder, and we'll explain. We'll talk about it tomorrow. Okay, so the limit is, I mean, exactly the same, meaning that the limit of the expected number of fixed points depends only on whether or not your element is a power and which power it is. Okay, it does not depend at all about gamma naught. On gamma naught. And the second part, okay, here for surfaces, you cannot expect to get a rational to get a rational function, but you get something which is almost as good. Namely, you get that the expected number of fixed points admits an asymptotic expansion. Namely, there are numbers, I call them A naught, A minus 1, A minus 2. They are all rational numbers, such that you can, for every natural number m, so the expected number of fixed points, you can write it as A naught plus A minus 1 n to the minus 1 plus A minus 2 n to the minus 2 up to A minus m n to the minus m. And then the error term is exactly what you expect. Okay, so this is called asymptotic expansion. So I get this, for every element, I get a sequence of number, or I get a series, but the series generally does not converge for any value of n. It doesn't converge, but any prefix gives you a very good approximation. It's similar to what you see in Taylor theorem in first year math. Okay, so, and so let me give you the analog examples. And with this, so what do you get for, I gave you the same words, but now A and the commutator, but now they are elements of this group. So it turns out that for A, and this will explain what you get, for example, is 1 plus 1 over n squared plus 2 over n cubed plus 10 over n to the 4. And then you can go on, but I stopped here. And for the commutator, you get 1 plus 2 over n. Okay. And actually, I didn't compute it more than the first term, but this is the kind of things that you get. Okay, so the plans for the, okay, this is the end of this talk. Tomorrow I will, the first part, I will show you how to prove this for the free group. And then we'll discuss what happens, what goes wrong when you try to apply the same method here, and why this is harder. And then we'll start, I'll start the crash course on representation theory, and we'll start seeing how to deal with the problem here. Okay, this is the plan for tomorrow. Thanks. Right. So there is, so for the eigenvalue of delta, if you use a Selberg's trace formula, you get, it gives you a dictionary between estimates on the eigenvalues of the Laplacian of this surface on the one hand, and some function on short closed geodesics on the other hand. So we want to analyze, and this function is based, you get a function on all closed geodesics, but only that depends only on the length, roughly only on the length of the geodesic. So what you need to know here, and we want to use this dictionary to study the spectrum. So we use this dictionary to translate the problem about eigenvalues of the Laplacian to questions about closed geodesics here. But what we said is that to analyze closed geodesics here in the cover, you can actually go over, you can translate it to a problem about closed geodesics here. So you go over all short closed geodesics here. But for each one of them, you need to know how many of them, for each one of them, how many geodesics here correspond to it. And for each one of them, this is, for delta, this is, the answer is that the number of geodesics here that project to delta are exactly the number of fixed points in the permutation corresponding to delta. So, yeah, so we use it, so these results, yeah, so this gives us a result for one closed geodesic. Then you need to work harder to make it uniform over all. You don't use just one geodesic, you use many of them. And then you need to work harder to make, yeah, all short ones, yeah. Yes, but still, I mean, the length of how short you need, you need longer and longer to get, especially when this n grows, you need longer and longer. I mean, the length should be roughly logarithmic in n. So you need to analyze longer and longer geodesics. So you need to work harder to get a uniform result on all these short geodesics and not just for one of them. Because here, for example, just as an example, if you use this result, you get that, okay, if it's a non-power, you get 1 plus O of 1 over n. But this O of 1 over n, the error term, what is the constant? This doesn't tell you anything about the constant, and you need to work hard to get a uniform constant for all. So only A0. In this result, only A0, which is the limit. So A0 is equal to the number of divisors of Q. We don't get anything about the other ones here. And this is basically this is one conjecture, one open question that I want to pose perhaps tomorrow is, okay, let's say you know this, what is the next, to understand what is the next term, what is the leading error term, what is the error term, this result? Yeah, but this is just because this comes from an analysis and it's. Yeah, right. By the way, in this model to go from here to here or to approach this, you probably need to understand better the next terms here. So if we understand better the next terms, we can probably improve this result from 316 to something higher. Because I mean, this is in the universal cover. This is 1/4 is the spectral gap in the universal cover in the hyperbolic plane. This is the ideal spectral gap, and you actually now we know, and we know that this is we can't get anything better than that. This is a result of Puder from the 70s, and now we know that this is so we know we can get this not for random models but for some surfaces, you know, you can actually get this. So we know that this is the optimal thing. And we expect that random things will behave like that just because, I know. This is what, no, also this happens, this is true in graphs, in the analog in graphs. And yeah, all the signs show us that this is what you should expect to get. Oh, you mean this? We just show that there are, no, it's not because, not because we have a control. We have this, no, we prove this result without any specific information about the AI. We just know that they exist. We don't know anything. It comes from the, I think it will be in the fourth part, in the fourth talk, perhaps, if I get there. I should explain roughly where we get this result from. Yes. So in the analysis in the Seber's trace formula, yeah, you can see that, yeah, if you look at, well, first of all, I mean, it's a bit tricky because if the square is also short enough, then you will also go over, delta square is also one of the geodesics that you get here. So, okay, but sorry, but you are right. No, because eventually we want to use this result. And so if when we look at delta square, we get something which is not 1. Actually, you can show that, okay, geodesics here, yeah, all the geodesics here that project to something which is a power, not primitive geodesic. This whole set is, in the Selberg formula, these are all negligible. You can throw them away and just deal with those that project to primitive geodesics. Yeah, so this is true, yeah. Yes, for Fuchs groups in general. Yeah, you can ask. Yeah, so I plan to say a bit more about what's open questions. So there's one more case where we know the answer, which is a free product of finite groups. so it's not exactly the same answer, but you get there are some interesting twists, but and basically for any other thing, for any other group, we don't know the answer, and not even perhaps not even for z squared. So even for z squared, for like a torus, we don't really know the answer. But I'll say more about it. No. This is true for any genus, at least 2. I talk about genus 2 just for the simplicity, but yeah, this result is true for any genus 2 or higher. Sorry, what? So yeah, so then the fundamental group is free. And you can use, okay, it's not exactly this, but so it's not exactly this method, but so it's related methods that were developed to deal with graphs. So now we can, so the results of Bordenave and Collins. There is now a very strong annals paper where they deal with homomorphism from free groups to, basically from free groups to SN, and they have very strong results there, and you can use that. You can use these results, and work a bit harder to get results about open surfaces with punctures, and this is what Michael and his student Will High did to show that eventually this is what they used to prove that there are surfaces, even closed surfaces. Okay, so you can get open surfaces with punctures with a good spectral gap, and then you can close together the punctures in a way that doesn't change a lot the spectral gap, so you can prove that there are closed surfaces with good spectral gap. Yeah, so this is basically known there.